Hi there, it's David Williams from the Electronic Engineering Technology Department at Okanagan College. This video is an introduction to AC analysis on single-stage bipolar junction transistor circuits. Quite a mouthful, but let's get on with it. So we see here a simple common emitter amplifier with a voltage divider bias. And I've brought it down here so I've got a little bit more white space to work with. Let's put some numbers into this circuit so we can work with some actual figures. Let's say we've got a voltage source here of 20 volts. We have a resistor here, one of our voltage divider resistors. This one's 50 kilo ohms, and let's make this one 10 kilo ohms. Let's not worry about what the actual values from the AC signal are. Let's just focus on the resistors that are creating the DC biasing point as well as creating the AC amplifier characteristics. The resistor here at the collector is 3 kilo ohms, and the resistor down here connected to the emitter is 1 kilo ohm. And actually, let's make this voltage source 22 volts. Now, the AC analysis of this circuit is going to involve figuring out what the gain of the circuit is, what the input impedance is, what the output impedance is, to give us an overall picture of what characteristics this circuit has as an amplifier. But before you get into the AC analysis, you'll notice that this part, all within here, the two resistors biasing the base, the resistor at the emitter, the resistor at the collector, and the DC voltage source, these are all DC biasing. This is a DC biasing circuit that you've hopefully seen already. So we actually need to do a DC analysis on this circuit before we can get into the AC analysis. We need to make sure that we are at an operating region that will allow this circuit to be an amplifier, so that it's in the right operating region. And to be an amplifier, you need to be in the active region. So I'm not going to go through and do all the calculations or show all the calculations for what the DC analysis is, but what we would find out is the voltage here at the base is about 3.67 volts. The voltage here at the collector is about 13.1 volts. Voltage down here at the emitter is about 2.97 volts. The collector current and the emitter current are about the same value at 2.97 milliamps, and the voltage between the collector and the emitter is about 10.13 volts. So if you go through this, you'll notice that the method that I used was the approximate method, that's assuming that the base current is effectively 0 amps. So that this R1 and R2 is truly a voltage divider. That 22 volts gets divided between the 50 kilo ohm and the 10 kilo ohm resistor. Now that we have the DC biasing point, we see that it is in the active region. This transistor is biased to the active region, and we can add an AC signal, apply it here at the base. This is our input signal. The circuit's going to act like an amplifier and give us an output signal that's going to be applied across the load here. And now our circuit can do something useful. It can be an amplifier. Now what happens is this AC signal here gets superimposed upon the DC voltage, the DC biasing point here at the base. And the way that works is this capacitor C1 couples in the AC signal, but at the same time it blocks the DC signal from affecting the signal outside of the amplifier circuit. And the reason that works is the reactance of this capacitor to the DC portion of the circuit is, well, reactance of any capacitor is 1 over 2 pi times the frequency of the signal times the capacitance. So at DC, the frequency there is 0. So what that means is the capacitance, or the reactance of the capacitor, is going to approach infinity. So it's effectively an open circuit. And for an AC, as long as the AC frequency is high enough, the reactance is going to get closer and closer to zero. You can figure out what the exact reactance is if you know what the frequency of the signal is, and that's actually an important thing when you're doing a frequency analysis of your circuit. But what we're going to assume is that the frequency is high enough to make the capacitors in this circuit effectively shorts. So what's going on in the circuit? If we take a look at the base voltage there, and I'm going to use a notation here, a lowercase v with an uppercase b to designate the voltage at the base that is made up of the uppercase v, uppercase b, which is the DC portion of the signal, plus lowercase v, lowercase b, designating the AC portion of the signal. So this over here is the AC plus the DC portion of the signal. And if we were to look at this on an oscilloscope, if this is our ground or 0 volt reference, the DC part of the signal is going to be at about 3.67 volts or so, and superimposed on top of that will be the AC portion of the signal. So the red is indicating the actual signal, and you'll just notice that it is offset by the DC value at the base. Similarly, the actual signal that I would measure at the collector, made up of the DC portion of the voltage at the collector plus the AC portion of the voltage at the collector, is going to give me a signal that is offset way up here at 13.1 volts, and the AC part of the signal is going to be centered around that 13.1 volts. So you see that we have a fair amount of offset to give this the actual signal at the collector. But then what happens is, to get to the output, we have a capacitor here that's coupling only the AC part of the signal across the load. So to get our output, which is measured here across the load, our V out is going to be only the AC portion of the collector voltage. So we have the same signal at V out as we have at the collector voltage, except instead of being centered around 13.1 volts, it's centered around our 0 volt reference. Now, in our analysis, in our AC analysis of a BJT circuit, we can use the principle of superposition to be able to separate out the DC portion of the analysis from the AC portion of the analysis. So I've already done the DC portion of the analysis here, and I can summarize what I did for the DC analysis. The first thing that I did was I ignored the AC sources, and really, technically speaking, I shorted the AC sources, the AC voltage sources. So that removes the AC source. Then I replace all of the capacitors with opens. Because once again, remember, the reactance of that capacitor, 1 over 2 pi Fc at DC, the frequency is 0. So the reactance of the capacitors approaches infinity. And then lastly, although this does take multiple steps, is find the Q point, find the operating point. Or, I mean, if I could go through and I could find all of the voltages and all of the currents in this circuit. For the AC analysis, what I want to do is come up with the amplifier parameters, so things like the voltage gain, the input impedance, and the output impedance. To do that, to do the AC analysis, there's also a number of steps that I'm going to go through. First of all, I want to eliminate the DC portion of the circuit. So I'm going to eliminate the DC sources. These are all voltage sources, so I'm going to short all the DC voltage sources. Secondly, I am going to replace all of the capacitors with shorts. I'm assuming that I'm at appropriate frequency and appropriate capacitor values that I can do that. Replace the capacitors with short circuits. Third, I'm going to simplify the circuit. And this is going to involve a couple of things. I'm going to do a couple of examples here. So simplifying the circuit might involve things like combining resistors to give the equivalent parallel resistance. So combining resistors. But more importantly, I want to know how this transistor behaves when the AC signal is applied to it. So I'm going to come up with a model for that behavior, and I'm going to replace that transistor with the model. And then my last step is to find the amplifier parameters. Okay, so the first thing that I'm going to do in my AC analysis is I'm going to short this VCC, and what that means is that this point here is going to be shorted to ground, so that point is ground. The next thing I'm going to do is short all of the capacitors, so that becomes a short, that becomes a short, that becomes a short. One of the really important things that happened here is by connecting this C2 across the resistor here that's connected to the emitter, is I have effectively removed the RE from the AC analysis. And then the last thing I'm going to do, well, actually let's redraw this circuit. So I've got my voltage source, my AC source here. I've got this resistor, RG. I have R1, which was always connected to ground. I have, this would be R2, which was always connected to ground. I also have R1, which is now connected to ground because I shorted the VCC. Then I go into my transistor. I'm going to draw it as a box for the moment. Goes into my transistor at the base. Over here at the emitter, I've shorted the RE. So the emitter is just connected straight to ground from the AC point of view. And then over here at the collector, I have my RC connected to ground now, because again the voltage source was shorted to ground, and I have my load connected to ground. Now, if desired, I could simplify this a little bit more. I could combine these two resistors to make one equivalent resistor of R1 in parallel to R2, and I could also combine RC and RL into one equivalent resistor and make it the equivalent RC parallel to RL. The other thing that I need to do is figure out the AC model, or determine which AC model I'm going to use for my BJT. The simplest model, and one that is quite effective at modeling a transistor, especially at lower frequencies, is called the T equivalent model. It has other names as well, but one of the names is the T equivalent model, and that model looks like this. I've got a base, and going down to the emitter, I have this what I call the little RE connected to the emitter, and then over here at the collector, I have a current source, And that current source is equal to beta times little IB. So depending on the base current, depending on the beta, this current source is going to create that amount of current. And that little RE value is equal to 26 millivolts divided by the value of the emitter current, the DC value of the emitter current. And where this value comes from, this is the operating point of this forward bias transistor, or forward bias PN junction. And at that particular operating point, there's going to be a certain amount of resistance, and that's what the little RE represents. So if I draw this inside my AC analysis model here, got the base connected to the emitter with the little RE, and connected to this current source. It's beta times IB. The next thing that I would do, now that I have my model, my AC model of the circuit, is to calculate what the gain of the circuit is, to calculate what the input impedance of the circuit, to calculate the output impedance of the circuit. But I'm going to save that for another video. I hope you learned a little bit about AC analysis, and I'll see you in the next video.